Hello again. In this video, we're going to go over the second part of 2.5, which is about limits at infinity. And specifically in this video, we're going to look at what are known as infinite limits at infinity. And so let me explain what we mean by that. Let's say you have this function x cubed. The graph of it looks like this. And let's say you want to find the limit of this function as x heads towards infinity. Okay, so as x heads towards infinity, let's look at what the y value is doing. So I think you can see as x heads towards infinity, the y value is heading towards infinity as well. So the limit of this function as x heads towards infinity happens to be infinity. And so this limit at infinity is infinite. And that's what we mean by an infinite limit at infinity. Now this is also called the end behavior of the function. The end behavior of this function is that the y value heads towards infinity as x heads towards infinity. And I'm just going to call that as you head towards the right, the end behavior is up. Okay, let's look at the end behavior as you head towards the left. So what happens to the y value as x heads towards negative infinity? Okay, well, let's see. As x heads towards negative infinity, I think you can see that the corresponding y value is also heading towards negative infinity. So the end behavior towards the left is said to be negative infinity, whereas the end behavior towards the right is positive infinity. If you would write this out as a limit, you would say the limit as x heads towards negative infinity for the function equals negative infinity. And so this is another example where you have a limit at infinity, negative infinity, a limit at infinity that is equal to infinity, negative infinity. Okay, so that's what we mean by an infinite limit at infinity. But what I really think you should focus on is you should think of this as end behavior. End behavior refers to what happens to the y value as x gets large and heads towards positive infinity. And it also refers to the y value of the function as x gets small and heads towards negative infinity. Okay, so we're going to focus in on this idea of end behavior for functions. Now, in order to do that, it's important to look at these cases here. There's two very important cases that we're going to look at. So the first one I'm going to look at is, suppose this was x squared, right? We had the function x squared. The graph of x squared looks like this. What's the end behavior for x squared? Well, as x heads towards positive infinity, it looks like the y value is heading towards positive infinity as well. So the end behavior is up on the right, whereas the end behavior on the left is up on the left as well. So as x heads towards negative infinity, the y value also heads towards positive infinity. So it's up on both sides, right? That's the way you would describe the end behavior of this function. But notice that this is true for any even power. So if this was y equal x to the fourth, the end behavior is up on both sides also. So it's really a product of the fact that the exponent here is even. And n is positive. Okay, we're assuming that this exponent is a positive and is even. As long as it's positive and it's even, then the end behavior will be up on both sides. Now, if it's odd, okay, so we've already looked at x cubed. Okay, but referring to x cubed again, the end behavior was up on the right and down on the left. Okay, again, we're assuming n is positive here as well, okay? So, but that's true for any odd. So x to the fifth would look like this. Notice it's up on the right and it's down on the left. So there's a pattern here, okay? For positive even exponents, the end behavior is up on the right on both sides, on the right and the left. And for exponents that are positive and odd, it's up on the right and down on the left. Now, one thing I want to caution you about is you can multiply these by coefficients that will alter the end behavior. So for example, if this was multiplied by a -7 in front of it, so -7x to the 6th, that what that negative number would do is it actually flips this over and the end behavior would be down on both sides. If you were to multiply this by a negative number like -7, that would also flip this. So the end behavior on this side would be up like this, and the end behavior on this side would be down. So multiplying by a negative coefficient would flip the behavior, the end behavior of these. So just be aware of that. Okay, so having said that, let's look at theorem 2.6. In this theorem, we're assuming n is a positive integer and p is a polynomial. And notice here they've written the polynomial in general form. This is the general way of writing a polynomial. This polynomial happens to have a degree of n. That's the degree of this polynomial. And this is the leading term of the polynomial. Now, in front of x to the n power, the coefficient in front of it is labeled as a sub n. Okay, that's the coefficient in front of x sub n. The coefficient in front of x to the n minus 1 is labeled as a sub n minus 1. Until you get to the last few terms of this polynomial, and you can see that the coefficient in front of x squared is labeled as a sub 2. The coefficient in front of x raised to the first power is a sub 1. And then the constant term is being labeled as a sub 0. So this is just a general way of writing a polynomial of degree n. Okay, so having said that, the first two statements of this theorem we already are aware of. If n is even, then the end behavior is infinity on both sides, right? As x goes to positive infinity or negative infinity, the y value is going to head towards infinity, which is up on both sides, right? That means the end behavior is up on both sides. But if n is odd, then the end behavior on the right side as x goes to infinity would be up because this is equal to infinity. Whereas on the left side, as x heads towards negative infinity, it would be downward, right? Because the y value is heading towards negative infinity. So we already know that. Now, if you take 1 over x to the n power and find the limit as x heads towards infinity or negative infinity, what's going to happen to the y value? Well, it's going to head towards 0 because what's happening here is x is getting larger and larger. You're raising that to the nth power. And so you get a number 1 divided by a really large number, which is close to 0. And by the way, this is still true if this was a negative number. So if you head towards negative infinity, you get 1 over a really negative number, but that still heads towards 0. Okay, so the limit of 1 over x to the n power as x heads towards either infinity or negative infinity is equal to 0. Okay, and then the fourth statement tells us what happens as x heads towards plus or minus infinity for a polynomial function. Now, for a polynomial function, you have several terms in a polynomial function, but the leading term, right, the leading term is this term here. The leading term actually dominates all the other terms. So as x gets larger and larger, this is the term that's going to be the largest. And it's going to be so much larger at some point that you can almost ignore the other terms because they become insignificant compared to the magnitude of this leading term. And so if you want to find the limit of a polynomial as x heads towards infinity or negative infinity, what you really need to do is just focus in on the leading term and see what happens to the leading term as x heads towards infinity or negative infinity. And that's what this is telling us. Now notice they do mention that this limit is either going to be positive infinity or negative infinity, and that depends on the degree of this polynomial, the leading term, the degree of the leading term, but it also depends on the sign of the coefficient of the leading term, a sub n. Okay, so let's look at an example where we would use this. So let's look at both a and b here. We're going to find the limit as x heads towards infinity and negative infinity for both of these polynomials. Okay, so let's start with part A. Let's let x head towards infinity and find the limit of this polynomial. Well, according to the fourth part of the previous theorem, we just need to look at the leading term. The leading term dominates. Okay, so let's just look at the limit of 3x to the fourth power as x heads towards infinity. Well, I think you can see as x gets larger and larger, x to the fourth is just going to get larger and larger. And then when you multiply that by a positive 3, it's still going to continue to just get larger and larger. So this would head towards infinity. But if x heads toward negative infinity, now again, we're trying to find the limit of this polynomial, it's sufficient to look at the leading term. So what's happening as x heads towards negative infinity? What's happening to this leading term now? Well, you're plugging in negative numbers now. You're raising them to the fourth power. When you raise them to the fourth power, they become positive numbers. And then when you multiply them by 3, they remain positive. And so I think you can see that as x heads towards negative infinity, this 3x to the fourth actually heads towards positive infinity. And you can see this from the graph. If you graph this polynomial, the graph of this polynomial looks like this. And you can see that the end behavior on the right is up, and the end behavior on the left is also up. And so as x heads towards infinity, the y value heads towards infinity, which would be up on the right. And as x heads towards negative infinity, the y value heads towards positive infinity, which is the end behavior on the left. So the end behavior on the left is up as well. Okay, so let's look at the part B. So now we want to find the limit of this polynomial as x heads towards infinity and negative infinity. And again, it's sufficient to look at the leading term, which in this case is negative 2x cubed. So what's happening to x cubed as x heads towards infinity? Well, 10 cubed, 100 cubed, 1,000 cubed, that's just going to get larger and larger as a positive number. But then you're going to multiply that by negative 2, and so actually it's going to become more and more negative. And so this is going to head towards negative infinity. Okay. What about when x is heading towards negative infinity? Well, this leading term here, you're going to be plugging in negative numbers now in for x, like negative 10, negative 100, negative 1,000. So negative 10 cubed, though, when you cube a negative number, you get a negative number back because you're multiplying a negative by itself an odd number of times. And so this x cubed is going to get closer and closer to negative infinity. But then you're going to multiply that by this negative 2. So a negative times a negative would be a positive. So overall, this is actually heading towards positive infinity. And so you can see this from the graph. The graph of this polynomial looks like this. The end behavior on the right is down towards negative infinity, and the end behavior on the left is up towards positive infinity, which matches what we discovered here. Okay, so I think it's important for you to get familiar with this idea of end behavior. And in this particular video, we focused in on the end behavior for polynomials exclusively. In the next video, we're going to look at the end behavior for rational functions. Okay, so hopefully you'll get a chance to look at that video as well. Okay, thank you for watching. Bye-bye.